At the end of class today, we were talking about a coaxial cable, and I just wanted to include a picture, just in case you were still puzzled as to what I was talking about. In this picture is the coaxial cable, and you can see the copper inner piece. It might be a little hard to see, but that's the inner conductor, and then the outer conductor is the part that you can use to screw on to the coaxial connection in the back of your TV, for example. So this cable is two cylindrical conductors, one with a small radius and one with a larger radius. The inner one is not hollow, the outer one is. Doesn't matter, doesn't change anything. They're both conductors, so the charge will still reside on their surfaces. And on a capacitor, typically we're talking about a system that has a net charge of 0, so we'll have the same amount of charge on the inner conductor as the outer conductor, just with an opposite sign, Q and minus Q. So I've included a picture here that illustrates a little bit about the geometry of the situation here. We've got two concentric conductors. They for reasons which you may see later, we need to have them on the same center. And the inner conductor has a radius r inner. I show, maybe don't get confused between diameter and radius, but it has a radius r inner, and the outer conductor has a radius r outer. And when I say the radius r out, that's r out is the radius to the inner part of the outer conductor, because that's where the charge is going to reside, right? The charge, according to Gauss's law, is all going to reside on the outside of the inner conductor and the inside of the outer conductor, minus Q and plus Q. Let me just correct myself here. I corrected the picture. The inner conductor is solid, and of course that inner radius is to the outside of that inner cylinder. Okay, anyway, too many inners, outers, and all. But this is the coaxial cable, and this is the coaxial capacitor, and I want to know what the capacitance is. And actually, when you think about it, and we'll see this in the end, the longer the cable is, the bigger the capacitance, right? Because if it's twice as long, it should be able to store twice as much charge for a given voltage, because it's got twice as much surface area. So we sometimes talk about the capacitance per unit length. If we double the length, it's double the capacitance, etc. But we can write the capacitance in terms of length, or we can just write the capacitance per unit length. So anyway, let's not worry about that, and let's just write down the capacitance. So the capacitance is going to be the absolute value of the charge divided by the potential difference between the two surfaces. So we need to calculate the potential difference between the two surfaces. So we need to know delta V. Well, we know that delta V is equal to minus the integral of E dot ds. I do not need to review how to do E dot ds here, because you have it in your notes and it's in the book. And you need to review that. You definitely need to review it. You need to understand where this comes from. But we're going to use the electric field of a cylindrical conductor, and which we've calculated before, and we're now going to integrate it with respect to radius. Now remember, if you look back in your notes, that the electric field is related to lambda, which is the charge per unit length. Hence, we're going to get capacitance per unit length. But it's related to the charge per unit length lambda. And we're going to do this integral from, we want to know the potential difference between the inner radius and the outer radius. So it's from R in to R out. And so we're going to go ahead and do this integral. We've done this integral before. We figured this out. Look in your notes. Look in the book. We've done this integral. But this is some calculus that you really should know, which is that the integral, lambda, 2, pi, epsilon 0 are all constants, and so they can come out of the integral, and then we just got 1 over r dr. There's a minus sign out front, but 1 over r dr, and the integral of 1 over r dr is the natural log of r. ... We did this in class. We end up getting the potential difference between the outer and the inner conductor is this. Let me do a little bit of an aside here. Has nothing to do with what we're doing here. It only has to do with the date today. Today is 314. Whoops, that's a 4. 314, which is, as you know, Pi Day. Sadly, most of you missed the Pi at the Pi Run tonight at 6 p.m. I know that only maybe one person from class was there, but that's okay. Anyway, so what's interesting about pi, again, it has nothing to do with capacitance, but it is Pi Day. And what's interesting about pi is that, remember that pi is defined as the circumference of a circle divided by the diameter of the circle. So it has to do with the geometry of the circle. That's where pi comes from. It's an interesting number in a lot of ways, but what's particularly interesting is to think about where pi shows up. Look, there's a pi in delta V, but what does delta V have to do with circles, right? I mean, pi was in delta V for point charges, cylindrical charges, but not planes of charges. So point charges and cylindrical charges, I guess, could have some indirect relationship to circles, right? Spherical symmetry for the point charge, cylindrical symmetry, which has a circle at one end. So, but it's interesting where pi shows up when we're not anywhere close to talking about the geometry of a circle. Okay, so anyway, let's get back to the capacitance. So if we just plug that delta V into the definition of capacitance, we get this quantity here. And then remember that lambda is charge per unit length. So I will now simplify, remembering that lambda is charge per unit length, to get the capacitance of a cylindrical capacitor is 2 pi epsilon 0 L over the natural log of the ratio of their radii. So that was just an example of, you can find the capacitance for anything. All you need to do is, if you know the electric field as a function of distance from the between the two objects, then you can calculate delta V using the definition of delta V, and then using the definition of C, you can use, right, C equals Q over delta V equals the integral minus the integral of E dot ds, etc. You can use these together to figure out the capacitance. If you know delta V or if you know E, then you know the capacitance. So it doesn't, for any geometry. And notice that what's in the box, which is the result, is dependent on the length L, like we said, twice the length, twice the capacitance. It's got more places to put charges. Or we can talk about the capacitance per unit length, as written in purple here. Okay, so what do you call a deer with no eyes? And what do you call a deer with no eyes and no legs? Okay, back to capacitance. So let's go back to the parallel plate capacitor. Easier to deal with. We don't have to deal with natural logs. That's really why. When we're talking about some qualitative stuff about capacitors. So let's just think about the parallel plate capacitor. I'm just going to write down a couple equations. Okay, so I've just written down everything twice. The general definition of capacitance and the capacitance in particular for a parallel plate capacitor. And then I drew a picture. And I said, let's say that we start with a certain potential difference across the parallel plates, delta V 0. And let's say that the parallel plates are a distance d0, d initial, apart, and therefore they have a charge q0 and minus q0 on the two plates. So I've written everything with the subscripts of 0. We're not going to change the area of the plate, so I'm not going to put a subscript on the area of the plate. So now, here's a thought question for you. Or you can even calculate it. While I'm in this situation where the capacitor is attached to the battery with voltage delta V0 across it, what if I separate the plates while it's attached? Right? Imagine the demo I had in class, and I just separate the plates while it's attached to the power supply. What changes? What are the new capacitance, charge on the plates, and delta V? First of all, let's just make sure we understand that really what's given, and I've drawn more than what's given quantities are, we've hooked it up to a certain potential, delta V0. We know its capacitance C0 because we can calculate it from epsilon 0 A over D0. And D0, therefore, is given. So these are the given quantities. So we can calculate, right? We can calculate Q0. Q0 is C0 delta V0. That comes from, hopefully, obviously, from that equation. Okay, so now I want to know what are the new capacitance, charge on plates, and delta V. Well, what changes? D changes, right? So I've just circled it here in the equation, right? D0 changes. Epsilon 0 and A don't change. So there's a new capacitance. What happens to the... and I also meant to ask the question, not only what are the new capacitance, charge, and delta V, but do they go up, down, or stay the same? Well, so now looking at the equation just for the capacitance, CF, right, has a new... is epsilon 0, A don't change, DF. Since DF is bigger than it was before, because I told you it gets bigger, therefore CF gets smaller. So the capacitance goes down, and the value is epsilon 0 A over DF. Okay, but now what about QF and delta VF? Think about it. CF is also equal to QF over delta VF. So if CF goes down, well, QF could go down, or delta VF could go up, or both. Or QF could go up, and delta VF could go up even more. So what happens to them? Well, what you have to recognize is that the capacitor is still attached to the battery, which has a potential of delta V0. By separating the plates, we don't change the voltage of the battery, so delta VF is still equal to delta V0 because it's still attached to the battery. And the potential difference across the capacitor. Notice that this is, and we talked about this before, but I want to remind you that this is the potential difference across the capacitor, not the potential difference of the battery. It just happens to be equal to the potential difference of the battery in this case because it's the only thing in the circuit. But if there was something else in the circuit, the potential difference across the capacitor isn't necessarily a potential difference across the battery. This is always, this quantity that has the two arrows under it, is always the potential difference across the capacitor. In this case, the potential difference across the capacitor must equal the potential difference across the battery. The battery doesn't change. We haven't changed the battery in any way. So delta VF is equal to delta V0, it stays the same. So that then tells us if delta V stays the same and CF goes down, then what happens to QF? Again, if delta V stays the same and CF goes down, we already determined that, then that means that QF must go down. The charge on the plates must be smaller. The capacitance gets smaller, the charge gets smaller, in this case. So you should think, again, we need to understand what's going on. We can't just use equations. What's going on is that we're grabbing onto these parallel plates and we're separating them. I'm doing this motion with my hands. I know you can't see it. We're grabbing onto these plates and we're separating them. And so physically what's happening is we're reducing the capacitance because by definition capacitance has to do with how far away the plates are, and it's smaller when they're farther away because the charges can't interact as much. But where do the charges go? The charge goes down. Where do the charges go? Well, they must actually go back to the battery. They go back to the battery. Because what happens is as we try to separate the plates is, well, actually, we'll talk about that in a second. But anyway, the charges have to go somewhere. They don't just disappear, right? So they're going to go back to the battery and the charge goes down. So here's a summary. It's a summary of everything we just said about that particular situation, about the capacitance, about the delta V, and now about the charge. That's a summary. So now let me ask a second question about this. Let's take the same situation. I'm going to draw the picture again. So this is a summary. So if we have an initial D0 and delta V0, then that allows us to calculate Q0 and C0 from these equations. So now the question is what if I have this situation where we're initially at D0, initially D equals D0. I charge the plates, charge the capacitor, and then detach the battery. So it's a different situation. We're going to detach the battery. So what we have is this situation here where we've got a capacitor attached to nothing. It's got plus Q0 on one plate, minus Q0 on the other plate, and it's got D0 distance between the plates. Again, A is the area of the plates that doesn't change. Okay, so now what happens if I separate the capacitor plates? So I'm going to grab onto the capacitor plates with my hands, and I'm going to separate the plates, and without touching them so that I get a shock, and ask what changes and what remains the same. So I wrote, if I increase D to DF, what changes and how? What changes and what is the quantity? Like, write down the quantity, the new quantity. Well, so since capacitance is dependent on the geometry, if DF gets bigger, then capacitance gets smaller. And the new capacitance is epsilon 0 A over DF. Nothing changes there, right? I mean, the capacitance is dependent on the geometry, not on the charge and the potential difference. Okay, so capacitance still gets smaller. But what about QF and delta VF? The potential difference across the capacitor. The charge on the capacitor and the potential difference across the capacitor. How do they change? Well, CF is equal to QF over delta VF. That's the definition of capacitance. But again, if CF goes down, does QF go down or does delta VF go down? Or does QF go down more than delta VF goes down? Does delta VF go up and QF goes down? Right, so that's what I really meant to say. Does delta VF go up or does QF go down in order to make CF go down? Or some other combination that makes CF still go down? Well, we have to ask what remains the same in this case. Well, we're not attached to a battery, so the potential difference doesn't have to remain the same. There's nothing fixing the potential difference. But the charge must remain the same. Because why? Because there's nowhere for the charge to go. The charge can't go back to the battery. It's not attached to a battery anymore. It's not attached to a closed loop. You cannot flow charge through a closed loop. So QF equals Q0. Q doesn't change. So what can we conclude? Whoops, let me undo that. What can we conclude about how Q and delta V changes? Well, Q we just said doesn't change, so therefore delta V must change, because since CF goes down, since C goes down to CF, therefore delta V must go up. In order to make this mathematics work, in order to make this equation work, then if C goes down and QF is the same, then delta V must go up. Okay, so some of you are saying, okay, it works. That works out. I get it. I can plug into an equation. But others of you are saying, whoa. That's okay, but it seems a little strange because isn't delta V something like energy? It's something like energy. And how is it by reducing the capacitance, somehow the energy is going up? Delta V is like energy. It's energy per unit charge. So the energy is going up. It is. And how is it the energy is going up? And we'll do a calculation, an actual calculation of energy pretty soon. But how is it the energy is going up? And what you got to realize is that in order to change the potential energy, because remember delta V is potential energy per unit charge, you got to do work. Was any work done when we separated the plates? Was any work done? If positive work was done, then we've increased the potential energy, right? That's what it means to increase the potential energy. It's when the external force does... Oops, wait, I got that wrong. No, I actually got it right. So it's when you increase the potential energy, the electric potential energy in this case, if the electric field does negative work. But in order for the electric field to do negative work, an external force has to do positive work. In order for the electric field to do negative work, an external force must therefore do positive work. And so if an external force does positive work, you increase the potential energy. If that doesn't make any sense to you, just simply think about lifting a mass, lifting your book off the table. When you lift the book off the table, the potential energy goes up if you lift it upwards. And now think about who does work. You're the external force. You are lifting it up. You're pushing in the direction that it moves, you're doing positive work, gravity's doing negative work. So to increase the potential energy, the external force does positive work, and the gravity does negative work. So in this case, the external force of me pulling the plates apart, that's why I'm doing the motion that you can't see, me pulling the plates apart, that positive work increases the potential energy of the plates. Oh, why do I have to do work? The plates don't just fall apart. Why do I have to do work? Think about it for a second. Why do I have to do work in order to pull the plates apart? Because the plates are oppositely charged and they're attracted to each other. The plates want to naturally go further together. So I have to do work to separate them. So if instead D got smaller, everything would go all your signs would change. If instead D got smaller, then I would be doing an external negative work, and therefore delta V must go down because the electric field is doing positive work in that case. And so if the electric field does positive work, that's like something falling in the Earth's gravity, where the gravitational force does positive work, and the potential energy would go down. Okay, new topic, quick topic. We've talked about putting insulators in between capacitor plates, which actually you almost always really have to do. Certainly air is an insulator, but when you're making capacitors that you use in the lab, you typically would put an insulator between them so the plates can't short. And when you put an insulator between the plates, it's called a dielectric. A dielectric. Okay, here's my wonky picture of putting something between parallel plates. So we're going to put some kind of insulator, and we're going to ask, how does that affect the capacitance? And here's how. We say that the insulator has what's called a dielectric constant. Actually, before I talk about dielectric constant, let's just talk about the permittivity. We had already said that the permittivity is going to be something different than the permittivity of free space, and it's greater. So the smallest permittivity you can have is the permittivity of a vacuum. Air, as we said, is about 0.1% larger. But almost all other insulators are going to have a higher dielectric constant. So the dielectric constant is going to be bigger. And remember that since C is epsilon A over D, we said epsilon 0 for free space, but epsilon for if there's a material instead of free space. So the capacitance is going to be higher. With an insulator, or what we call a dielectric between the plates. So hey, I think it's pretty obvious that we might want to increase the capacitance. We might want to find a bigger and bigger capacitance so we can store more and more energy. So it actually helps. It helps to keep the plates from touching, but it also helps increase the capacitance by putting a dielectric between the plates. And we characterize this, what's called we characterize these permittivities. Epsilon is equal to what's called the dielectric constant. Let me rewrite that. So we characterize the insulator by either the permittivity or a dielectric constant, where the dielectric constant, you can write K, but it's kappa. It's the Greek letter kappa, where the permittivity of the material is equal to some constant times the permittivity of free space. So kappa is what's called a dielectric constant. And the reason why we, rather than just always using permittivity, we use kappa is because if I have the capacitance of an air-filled capacitor, and I say that that's just the permittivity of free space, our capacitor has an area A, it's place of portion D, then the capacitance is epsilon 0 A over D. We can call that C0. Our new capacitance C, with the same capacitor where I filled the space with some yellow, ugly slab of plastic with a permittivity of epsilon, which is different than epsilon 0. Well, if I know I can take the ratio of epsilon over epsilon 0, then all the dielectric does is it increases the capacitance from when it had vacuum or air in between. It increases it by a factor of kappa. So that's why we use kappa instead of epsilon, because now we can show how the capacitance changes when I put a dielectric between the plates. And this is true for any geometry. So this is, I don't know if I call it a definition, but it's not for a particular geometry. This is true for any geometry. If I fill the space with a dielectric, with dielectric constant kappa, the new capacitance is kappa times whatever the old capacitance was, whatever the capacitance was, with nothing between the plates, or nothing in the empty space. A couple of quick things about dielectrics. First of all, what are the units of dielectric constant? Raise your hand and tell me, quick, what are the units? It must be unitless, right? Because it's just a ratio. Look back at the last 2 pages, it's just a ratio, so it must be unitless. And the other thing is why is it that if I put an insulator between parallel plates, it always increases the capacitance? That's basically what we've said, is that kappa is a constant. We implied is kappa is a constant greater than 1. And so the way we talked about it before, and so it always increases the capacitance, right? It always increases the capacitance to use dielectric. So why must that be the case? Well, if we think microscopically what's going on, let's say that this is a dielectric slab, right? So in a dielectric, a piece of plastic, a piece of glass, a piece of wood, an insulator. If it's neutral, right, it's going to be a neutral slab of plastic insulator. There's no reason for it to have any net charge in it, and most things are neutral. Well, what does it mean to be neutral? It doesn't mean it has no charges. It means that it's got the same number of positive and negative charges. So they're just randomly, sort of randomly distributed positive and negative charges. But actually, one of the things about nature is that if it's neutral, what it really means is that in most cases, the thing is filled with dipoles, right? A plus and a minus together, a plus and a minus together, a plus and a minus together. Oops, I lost some here. Plus and a minus together, plus and a minus together, plus. They are just randomly oriented dipoles is really what's going on. Because you think about if the thing is neutral, it's a bunch of neutral atoms. And neutral atoms really have a positive nucleus and the negative electron cloud, and it's a dipole. And so there's just some randomly oriented dipoles inside this neutral insulator. There's no electric field until we do something to it. There's no potential difference. There's no net charge. But what happens when we put a dielectric between capacitor plates? When I put the dielectric between capacitor plates, I'm going to try to draw this as I go. If I put it between capacitor plates, I'm going to put a capacitor plate here and a capacitor plate here. I'm going to keep those two-dimensional. And if I put plus Q on this plate and minus Q on this plate, I've now put this dielectric in electric field. The electric field points from plus to minus, right? So there's an electric field. So what is this electric field going to do to those dipoles? So now the picture is actually not valid because the electric field is going to, while it's not a conductor, the electric field is going to push on the positive charges and pull on the minus charges, push to the right on the positive charges, push to the left the minus charges. And so what's going to happen to those dipoles? Sure, they're not going to move like they're in a conductor, but they're going to shift. And the dipoles are going to tend to line up in the field. I've shown this schematically here. Sure, they're not going to line up this neatly because it's not a conductor. They're not going to move as easily, but they are going to shift a little bit, and they're going to line up sort of like this when you put them in an electric field. The bigger the external electric field, right, the bigger the voltage across the capacitor, the more they are going to line up. And look at the dielectric. The dielectric has more positive charges on the left and more minus charges on the right. Right? More positive charges on the left, more minus charges on the right. And so you've got a larger charge separation, right? Where before we had just separated plus Q from minus Q, we've now got a larger charge separation, right? We got more plus Qs on the left and more minus Qs on the right for the same potential difference. So the dielectric gives you a bigger electric field inside the capacitor. It gives you a bigger charge separation, and it gives you a bigger capacitance. So I want to do a problem, a typical capacitor problem and with a dielectric. But before I do that, let's just think about, let me give you an example of some dielectric constants Dielectric constants. You can look them up. Just Google it. You can dielectric constant of anything. You can have, I mean, there's all different kinds of plastic, but I'm looking at my computer. Mylar has a dielectric constant of approximately 3. Glass has a dielectric constant of approximately 10. It's actually relatively high. I mean, you can get a lot bigger, but they typically tend to run. For common materials, tend to run somewhere between 1 and 10. Vacuum. What's a vacuum? What's the dielectric constant of the vacuum? You should know this. It's 1, right? Because epsilon is epsilon 0 in that case. Dielectric constant of let's see, Mylar, glass, vacuum. What about water? Water? What do you mean water? Well, you could fill a capacitor with water, right? You could. You just have to make it waterproof, but you can fill it with water. Dielectric constant of water is actually pretty darn high. It's about 80. Those are just examples of dielectric constants. Okay, so now I'm going to ask 2 questions. I'm going to ask, what is the charge of the capacitor plates before I add a dielectric? And then if I add a dielectric, let's add water. If I fill the space between the plates with water, what's the new capacitance? And what else changes? What other physical quantity changes in the circuit? Okay, so I've redrawn my picture. I put a dielectric in it. We had the original quantities with no dielectric, and now we want to know the new capacitance. Well, this is trivial, right? The new capacitance is kappa times the old capacitance, so therefore the new capacitance, therefore the new capacitance is 240 microfarads, okay? So 240 microfarads. What else changes? Think about it. What other quantities change? Well, what are the other quantities we can talk about? Delta V, Q, and C, right? We can talk about delta V, Q, and C. What changes? Well, C goes up. Delta V remains the same because it's still attached to the battery. Delta V doesn't change. Adding the dielectric doesn't change delta V because it's still attached to the battery. And so if C goes up, then Q must go up, right? Charge per delta V. If C goes up, Q must go up. So Q and C go up, and delta V remains the same. So by how much does Q go up? Q must also go up. If C goes up by a factor of 80, then Q goes up by a factor of 80. We never calculated it initially, so we can say Q0 is C0 delta V. That's C equals Q over delta V, right? So Q0 is 3 times 9, 27 microcoulombs. A volt times a farad. They're both MKS units, gives you a coulomb. Don't be confused. This C right here is not capacitance. That's our unit. You got to look at context. So our new charge, Q, is the new capacitance times delta V, or is 80 times that, which gives us 2,160 or 2.16 millicoulombs of charge on each plate once I put in the new dielectric. Without writing down anything else, let's just think about, okay, so what would have happened if I didn't have the battery connected? So I charge the capacitor, and I get it charged up to 9 volts and 27 microcoulombs, and then I detach the battery, and then I put in the dielectric. What would happen if the battery wasn't attached? Just like the question we asked before about separating the plates. And think about what would change and what would remain the same. In that case, right, if we put in the dielectric, the capacitance still has to increase because it's just the physical quantities. The capacitance has to increase. The capacitance is still going to be 240 microfarads. But Q will remain the same because there's nowhere for the charges to go. The charges can't flow anywhere. It's an open circuit if there's no battery connected. So Q remains 27 microcoulombs. And so that means that for C to go up and Q to remain the same, then delta V must go down by a factor of 80. Delta V must go down. Okay, so I've indicated this in the corner, right? C goes up, Q remains the same, therefore delta V must go down because C is equal to Q over delta V. So delta V goes down by a factor of 80, whatever that ends up being. So actually, let's think about why it goes down. Or no, not why it goes down, but what's a result of the fact that it goes down. The fact that the potential energy goes down means that I didn't have to do any work to put this dielectric in the capacitor, right? It wanted to be there. Things go to their natural lowest potential energy. So if the potential energy is going to go down, then that means that I don't have to do any work to put the dielectric in there. In other words, if I just sort of put the dielectric nearby, it's going to just kind of get sucked in there, just like dropping a mass near the surface of the Earth. It'll take me work to remove it. If I remove it, delta V will go back up. And so therefore, I must have done work to remove it, just like I had to do work to separate the plates in the last problem. Okay, I think that's all we're going to do with dielectrics for now. There are two things left in this chapter. One is combinations of capacitors. What happens when you put two capacitors in series or two capacitors in parallel. We might wait to talk about that until we do circuits. I do have to remember to do that, but I might wait to talk about that until we do circuits. But the last thing we want to do, other than that, is energy stored in a capacitor. And it is a potential energy. So energy stored in a capacitor. So we call it U. And it's an electrical energy that's stored. And so we want to be able to calculate how much energy is stored. I'm going to do a really quick hand-wavy argument as to how much energy is stored in a capacitor. And the result is what's important. It's good to know how we get there, but the result is what's important. Remember what happens when we hook a battery up to a capacitor and we start to charge it. The first charges move through the circuit as if the capacitor isn't there. They move really with no resistance because wires theoretically have no resistance, ideally have no resistance. So it takes no work to move the first charge to the plates, right? To move the first proton, if protons moved, right, which we're pretending they do, to move the first electron to the negative plate and the first proton to the positive plate, or the first electron away from the positive plate. And then the second one takes a little more work because now we're pushing against the charges that are already there. The third charge takes a little more work because we're pushing against the charge that's already there. So on and so forth until the capacitor becomes fully charged, right? Until it's no longer charging. So think about, initially it takes no work to move the first charge. And the question is, how much work does it take to move the last charge, right? The very last charge. This is actually the same as asking, so remember, we've fully charged the plates and we're almost fully charged, and we're just taking the very last charge and we're moving it from one plate to the other through the circuit. But we are really just moving, if you think about what we're doing when we're charging a capacitor, is we are moving the charges from one plate to the other. We're taking the positive charges and moving them from the negative plate to the positive plate, or we're taking the negative charges and moving them from the the plates would be neutral to begin with. But really, by charging a capacitor, it's the same as if we're taking charges and moving them across the separation. So the question that I want to ask is, if a capacitor has a potential difference of delta V, how much energy does it take to move a charge Q through the distance delta V? And we know that the amount of energy is delta U equals Q delta V. So the very last charge takes an energy of Q delta V. The very first charge took an energy of 0 when delta V was 0 because there was no charge separation yet. When fully charged at the top, I won't write it all out. So therefore, what is the total energy stored in the plates? What's the total energy if the last charge allows the plates to be charged so that we got plus Q there and minus Q there, big Q. We were moving charges one at a time, little q's one at a time to get a big Q. It turns out to be the average of the amount of energy it took to move the first charge and the amount of energy to move the last charge. So the total potential energy, and we actually write it, rather than writing it as delta, we just write the total energy stored in the plates when we've got the full charge separation is 1/2 Q delta V. 1/2 Q delta V. I don't know if that was too hand-wavy for you, but it is 1/2 Q delta V is the energy stored in a capacitor. If you didn't like that, then let's just do the actual calculation, right? The amount of energy stored, I guess I made a mistake here, hold on. the amount of energy stored, U, is equal to the integral, right? So because we're charging it up, the charge is changing of V dq. And why is that the case? Why is this integral the case? The integral is true because of the definition of delta V equals delta U over Q. But since Q is changing as we charge it up, then we have to integrate from 0 to big Q of V dq. If we integrate that quantity, so now I'm going to integrate that quantity. I've written it all out here, but take it one step at a time. U equals the integral of V dq as we charge it from 0 to a total charge of plus Q, big Q. But V is dependent on Q, so we got to write V in terms of Q. So what we've written in the next step is V is equal to Q over C. That's the relates V, Q, and C. Now we've written the integral in terms of Q and a constant, because C is just a constant, right? C doesn't change. Q and V are changing as we're charging it up, but C doesn't change. C is a constant. So we can pull the C out in this third step, and so we've got 1 over C, integral of Q to Q. Do that integral, plug in the limits, big Q, 0 to big Q, and we get 1/2 Q squared over C. Oh, wait, but that's not what we said before. We said that it's 1/2 Q delta V squared. Well, actually, yes, both of those are correct, right? Because C is equal to Q over delta V. So therefore, because C is equal to Q over delta V, that is why these two are equal, because you can just go ahead and make that substitution for Q equals CV squared. Wait a second, which substitution are we making? Oh, C equals Q over delta V. Oops, sorry, shouldn't have had the squared here. That wasn't, whoops, that didn't belong. Sorry, so once again, we're going to make the substitution for C. Going to make the substitution for C, and so we get 1/2 Q delta V. And we can also write this in terms, right, we wrote it in terms of Q and C, Q and V. What if we just want to write it in terms of C and V? Again, making the substitution for Q in that second equation, we can get 1/2 C delta V squared. So we got 3 equations. It's sort of like saying V equals IR, and therefore I equals V over R, therefore, oh no, it's not the same. Oops. Sorry. Not the same because we're making a substitution, but regardless, we're combining 2 equations in order to get 3 different relationships for energy. Energy stored in a capacitor, 1/2 Q delta V, 1/2 Q squared over C, 1/2 C delta V squared. Don't memorize all 3 of them. You'll need one of them, but you also need to know the relationship between Q, delta V, and C, and then you can get the other 2. We'll pick up energy stored in a capacitor in class on Friday. So for now, adieu. Okay, matchstick problem. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 matchsticks, making up 4 squares. And I want you to make 3 squares of equal size by moving 3 sticks. Exactly 3 squares, moving exactly 3 sticks. Stop this if you want to think about it yourself. Here I go. I'm going to move this stick, I'm going to put them here and here. And I'm going to move the third stick. Hopefully you can see it now. I'm going to move this stick and put it here. So what we're left with is boop, 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 boop. I don't know. Maybe that's too easy. I don't know. Maybe it was hard. I don't really know because I looked at the solution. Oops.